Okay, so welcome to the last talk of Neutrino Frontiers, and we have the pleasure to have with us Georg Raffelt, who will tell us about particle physics and supernovae, past, present. You included present, huh? You
Pardon
told
me?
me past and future, but it's past, present, and future.
Oh no, I changed my title a little bit. So yeah,
So you will
when I
tell.
first submitted my title months ago, of course it was some generic
No,
idea,
it's a joke.
and but then when I found my talk, which is scheduled for 5 o'clock on Friday at the end of this marathon, I got very disheartened and thought nobody would want to hear yet another
No,
technical lecture. So I thought to be a little bit light on myself and everybody else, and
yes.
just make some general remarks on in the framework of the subject.
Sure.
Okay.
So thank you very much.
So what you're seeing here, of course, is the Duomo montaged before the Crab Nebula, and as you know, the Crab Nebula is the remnant of the supernova of 1054 that was reported in this ancient Chinese archive posting here. What these Chinese astronomers, of course, had no idea about is that this is actually a neutrino event. So this insight grew about 900, almost exactly 900 years later, with the work of Gamow and Schoenberg. The two of them in the 1941 papers interpreted a supernova with reference to the Crab Nebula actually as a neutrino event, and indeed introduced what we still now know as the Urca process for neutrino emission, which is these two beta reactions where you always lose energy no matter on which side the electron is. And so actually the name, they say, we just for brevity call it the Urca process and never explain why they call it that way. But it's called that way because it's named after this casino in Rio de Janeiro, where apparently the two of them first met. And so it was one of those jokes of slipping a funny term into physref pages, and the editors apparently didn't complain. It's a little bit like the penguin graphs of QCD. That is a similar example. So for penguin, yeah. But in this case, it was no bet. It's just they like the birds. Had just funny ideas. So that's how that's I think how it began. That one thinks of a supernova as a neutrino event. Of course, much of the details have changed, and but still the Urca name has stuck, and people never quite know what it means, and think it's an acronym for something. So of course, since that time we've learned a lot, and now we know what we like to call the grand unified neutrino spectrum on Earth, the neutrino sources from all the neutrino spectrum on Earth from all sources in the sky. So we've seen many such plots over this conference. I just want to point out two little details. That our plot is different from other people's plot. One thing is it is an immediate keV range where the solar thermal neutrinos come about, fill that previous gap between cosmic and nuclear neutrinos that nobody has yet ventured to detect, but are sort of the dominant flux in this intermediate keV-ish energy range. And all the cosmic background neutrinos are here shown with at least two spectral lines. So neutrinos are now non-relativistic. They're not radiation. They're hot dark matter. And so the neutrinos are actually in energy space a spectral line. And detecting them is, of course, one of the future ideas of measuring the cosmic background neutrinos in this non-relativistic sense. Okay, so we know a lot more about this. In fact, what's even more impressive is that these cosmic neutrino backgrounds, these neutrino backgrounds of Earth, are becoming a nuisance and a background for other people's experiments. So what's shown here is what's called now the neutrino fog, where the solar neutrinos and atmospheric neutrinos are close becoming a background to the measurement of dark matter particles. So in dark matter detectors, these solar atmospheric neutrinos are becoming a background to detection. So there's actual neutrino pollution in the sky for detecting dark matter. And so that reminds me of this old dictum that yesterday's sensation is today's calibration, and tomorrow's background. So this is an example for this old dictum coming true in a way which was unimaginable a few years ago. And in fact, what we heard from Francesco and during this conference is that in fact this has just happened for the first time. So in some parallel conference someplace else, people reported the first detection of a solar Bohr neutrino in one of these dark matter detectors. So this is a reality, which I think is an amazing development of this whole field of neutrino astrophysics or neutrino astronomy. Okay, but returning to supernova, so the big event of this whole field was, of course, the supernova 1987A, which was shown many times here in this conference, with about 24 neutrinos detected in three detectors that happened to be online at that time, and which still keep us busy today because it's the only case of detected supernova neutrinos. I just want to make yet another little historical comment. I mean, it's not a big surprise that this happened on 23rd of February and no other date, because that's Neutrino Day. And it's Neutrino Day because the very first natural neutrinos all detected on 23rd of February. 22 years later, at that time, people are looking for atmospheric neutrinos. So this one goes back to the group of Fred Rines, who was the original group detecting the reactor neutrinos in the 1950s, and they were looking in a very deep mine for atmospheric neutrinos, and another group in the Kola gold mines in yeah, underground. Yeah, Irvine. Yeah. And so this plaque is at the mine shaft today. It's written here. So that's a plaque on the mine shaft that was put there. It's just for those who are younger than this, to remind people of this history. Okay. But then when Supernova 97 happened, return to that, it was in 1987, and just to put it in historical context, the only other ongoing measurements of neutrinos from outside the Earth was, of course, the Homestake solar neutrino experiment, which took data over many decades and then told us about the solar neutrino problem, the first indication of neutrino flavor oscillations. But there was nothing else around at that time in terms of measurements. So you can imagine how sensational was the supernova neutrino detection. Returning to other important things happening around that time is that Smirnov and McCabe and Smirnov detected theoretically the adiabatic conversion of neutrinos. So actually, I prepared that slide 12 years ago for the Smirnov Fest for his 60th birthday. So that's Professor Smirnov, who gave a lecture here last week, and that's Oleg Mikheyev, who unfortunately has passed away quite a few years ago. And so it's just an illustration about the important things happening in just around the same time as the supernova was detected. So that idea that you could have a sort of avoided level crossing and then in this way get a large flavor conversion despite a small mixing angle. Of course, it's very ironic that in the end the correct solution of solution is a large mixing angle. But anyway, these ideas changed the whole discourse in those days. Yeah, right. So it's about 2 years before the supernova, right? So I want to make another comment in this context. Of course, now this MSW effect is taken to be for granted, and I think there's somehow an underappreciated aspect of this in terms of the Borexino experiment. I mean, here we see the survival probability of solar neutrinos as a function of energy, as measured by Borexino and other experiments, and we can see these vacuum oscillations here, which are for delta m square O2e large for small energies, and then the MSW conversions out here, and we can see that transition. And so what this kind of proves is that this whole stuff about meta refraction of neutrinos is actually experimentally verified. And I think this is a sort of underappreciated point of the Borexino experiment, about which we heard quite a bit at this conference, right? So I just want to pick up on this question. So when we talk about this refraction and maybe it's not just fantasy, it's proven physics, which may not be completely obvious at first. Yes, please. Yeah. No, I think that's the most. Maybe someone else can comment, but I think that's the most robust evidence that meta refraction of neutrinos, that neutrinos actually suffer refraction in medium, right? It's not completely obvious. It's of course it involves only standard physics. It should be true, but it's nice to be sure it's actually true. Yeah. Yeah, of course, the day-night effect is another aspect of this. But I mean, anyway, I just want to say something very positive about Brooks, which I think is important. And in my opinion, they would have deserved a Nobel Prize for something, right? But that's just my personal opinion. Yeah, but of course, neutrinos can interact coherently in other ways, not just in the forward direction, also in other directions. And so coherent neutrino scattering on a big nucleus strongly enhances the cross-section by n square. And this point was made in this paper of 1974 by Dan Friedman. So this effect, this coherent elastic neutrino nucleus scattering, the acronym you can write with, if you write the neutrino with a nu, then this looks like so the Americans call it seventh, and they always call this effect that way. And of course, this is a very important effect to trap the neutrinos when the supernova falls in, because the coherent enhancement lets the neutrinos not stream freely out. And so this, for neutrino trapping, this is a very important effect as mentioned in this paper. And now this is a big business. I mean, this is one connection between supernova and particle physics. Not everybody, many people now measure this effect in laboratory experiments. And of course, these dark matter experiments, where we just saw the 8 boron detection, is another example of that. And I just want to point out something like to show the citation history of a paper as a measure of activity in the field. You see this paper was barely cited at all for decades, and then there's this huge burst of citations, which has to do with the huge level of activity in this 7th measurements by many groups. So I think it's also one of these connections between particle physics and supernova physics, although it's not always expressed as such. Yes? Yeah. But I mean, if you look at the paper, I think I've been at one of these meetings. It's a community with many experiments, a huge enthusiasm. So it's an amazingly active field, right? And of course, this one boron neutrino that we heard about from Francesco is, of course, another example of this, right? Okay. Yeah, so more important things happened in the mid-1980s, except for some of us getting their PhD at that time. So one was the discovery of how supernovae actually explode. So this is the original publication of the delayed neutrino mechanism by Jim Wilson. And I was kind of surprised in the previous talk that people still discussed Jim Wilson's certain numerical assumptions. Anyway, what we are seeing here is this thing that the shock wave goes out and then hovers around and then goes out with a delayed mechanism. And that was found numerically by Jim Wilson, but then Hans Bethe helped to explain this analytically. And so that was the original sort of understanding of supernova explosions, which also goes back just a few years before the supernova 1987A. On the other hand, I want to make this point that in these models gave us neutrino spectra, which one should detect or interpret the supernova 87A data with. And so there was always this strange behavior in these models that, of course, we have the usual profile of the neutrino burst, but then the energies had this strange behavior of going up and up and up and up. So there was this huge hierarchy of predicted neutrino energies, which was very exciting to people looking for flavor oscillations. And even as Sergei pointed out in his talk, there was even a paper excluding some of the solar neutrino interpretations based on the 87A data. But this is completely wrong. It's completely unphysical. And one could convince oneself it's unphysical. And I'm just stressing this. I mean, this Livermore model, as it was called, has lived in the literature for a long time because people in the experimental community just kind of maybe wanted this to be true. And I prepared this slide for a meeting in Tokyo 30 years after supernova 87A in 2017. So this model was still going around in the literature at that time, and so I put this important gravestone that we should not pay attention to this anymore, because we now know, of course, it's not behaving. But we saw in another talk earlier this week a similar graph for the merging neutron stars, and I think the speaker said this was probably not complete or something. So I'm also showing these two graphs in connection with the debate we had here among some other people. That is, how much should you trust numerical results when you don't understand what's going on inside? So one can say, yeah, whatever comes out numerically comes out, and so that. But if you don't understand the physics behind it, we should be maybe skeptical. So here, that's an example where I think people are misled for a long time about what to expect from a supernova. Anyway, today we know much better, and I'm just flashing this, that supernova spectra have these different phases, the depolarization burst, the accretion phase, and the cooling phase, and they're never these large hierarchies of energies, and also not large hierarchies of fluxes. But of course, there are details that can be tested about flavor oscillations. I'm also referring to this paper where people sort of tell us what we could learn from next galactic supernova from these different phases. I would probably say that every sort of phase of the supernova is in itself a separate experiment. But shouldn't say about the integrated spectrum as we did for Super 87A. Every phase can tell us something else about something else, and what exactly we will learn will depend on what we see in the next galactic supernova. Maybe black hole formation, maybe fallback. And anyway, in the list of things we can learn, they mention a lot about flavor mixing and new physics. And so these are two points which I want to comment on a little more. So we now know a huge amount about neutrino flavor parameters. So in the precision air, we know almost everything. We have the mixing angles to sometimes percent precision, depending on which one exactly it is. And the mass ordering and CP violation almost certainly will come from the next generation experiments, as we have heard about in various talks at this meeting, right? And then also, not in our weeks, but the week before, people discussed this cosmological issues. There's that new DAISY result where we get neutrino mass bounds as a function, as function of some of the mass, of course, which are very restrictive, and even point to a negative mass. So maybe there's something unexplained going on about these analysis or data. But in any case, the cosmology provides us with the best in restrictive limits about about neutrino masses, and in the near future, hopefully, a real measurement of the neutrino mass from cosmology from the sky. So we should not hope for time of flight measurement from a supernova anymore. That's old hat at this point. On the other hand, having these small masses sort of assured is an interesting thing, because now it's basically certain that one can resolve fine time structure in the neutrino signal. So we've heard in some talks about the SASI mode in this hydrodynamic instability in the supernova models, and this will provide a modulation of the expected neutrino signal on these few millisecond timescales. And so if the neutrino mass are not too large, then you can't have a time of flight smearing out of this effect. So seeing the SASI mode in neutrinos, which one could do for like a supernova easily in IceCube and super or hyper Kamiokande, depending exactly on what's available at the time. So I think, to me, that's one of these very interesting observations that one could make in neutrinos about the supernova to learn really about the hydrodynamics that's going on there, which is not accessible otherwise. I think it's kind of fantastic that the hydro instabilities would imprint themselves on the neutrino signal. So that's something to wait for next galactic supernova. Right. Another thing that came out of the supernova 1987 that has to do a little bit with the propagation speed, has to do with this question: do neutrinos actually gravitate? So that's maybe a silly question, but nobody can measure it directly. Nobody has seen neutrinos being affected by gravitational fields. But with the supernova 87A neutrino, we can do it, because the neutrino signal and also the photon signal would suffer Shapiro time delay. And so the Shapiro time delay to large intergalactic clouds would be a few months. But the photon rise time and the neutrinos were observed within a few hours of each other. So you saw the neutrinos and photons arrive within a few hours, not within a few months. And therefore, this Shapiro time delay must affect both in the same way, within 10 to minus 3 or something. So that kind of proves that gravity affects neutrinos the same way it affects photons. A similar point was made not long ago by these merging neutron stars that were seen in gravitational waves and in gamma rays and so on. And so the gravitational chirp and the first gamma rays came within a few seconds of each other, proving the same point, but now between gravitational waves and photons in an even better way. So maybe this is very silly, even a very silly question to ask, but anyway, that's the answer. Yet more about neutrino propagation speed. Again, I have here a plot of the citations of the supernova neutrinos as detected in these experiments, a function of time. So a lot of activity first, and then not much and more later. And there's that big peak somewhere in 2012, which appeared at the time, and people observed this superluminal neutrino signal from the OPERA experiment. And then everybody said, but the supernova proves the opposite. Neutrinos are moving with the speed of light. So that's another example for information. But whenever it comes about propagation speed of neutrinos, the supernova 87A is still a very important laboratory. But let's turn to standard particle physics. So we have this beautiful standard model of particles with three families of particles, and of course most of standard everyday physics is dominated by the first family, the electron and the first family particles. Probably supernova is one of the few environments where all flavors play a role of neutrinos, and we'll return to the flavor conversion question later. Only recently, however, have people ventured to include 6 species neutrino transport as a new standard. Previously, all the mu tau, all the heavy lepton neutrinos were lumped into one species, and people had 3 species transport. And those of us not so close to the simulation always thought, the others are very similar, but they need not be very similar. That was just a practical approximation. And the other case now, the muons, the second generation, we always heard, muons are not important because the mass is so large, but 100 MeV is not large compared to a 30 MeV temperature, where the average energy is 100 MeV of everything. So there are lots of muons in supernova. Just somehow nobody ever told us, and so now this is called standard. It's becoming standard to include muons in a supernova. So the second generation plays a role in the supernova. Third, there is on the quark level, there's a strange quarks, which should be in the form of hyperons. So this is an open question. There's that so-called hyperon puzzle, which means these hyperons, these strange barons, should be in a supernova, but then the equation state would not allow the most massive neutron stars to exist. And so there's a bit of a tension here, and I guess we heard a lot about equation of state last week, but we did not. This was not addressed so much. I don't remember, but somehow maybe it's another of those best kept secrets which nobody talks about, but may still be important. So the second generation kind of becomes important in this context. Okay, but now let's briefly turn to some other topic beyond standard model. There's of course supernova can be of course a laboratory for beyond standard model physics for new particles, and there have been a huge number of papers written recently, and I can't review this. I just can mention the main arguments, which is that within the neutron star, one kind of energy transport and lepton number transport, maybe by stellar neutrinos that we heard, or by other particles, we can have energy transfer directly, or maybe help with the explosion, or maybe over-explode the supernova and get constraints in this way, or things can escape entirely and contribute to the cosmic background of axions, or by decays to photons. So many things that can happen with supernova sources, individual supernova or the diffuse supernova background. And as I say, so many things have been discussed about this recently that somebody should write a review, which would be very broad, I'm afraid. I restrict myself to the basic case of axions, and just limit myself to the, at that time, basic argument of the so-called cooling bound. So here the idea is that if axion or something else can directly escape from the inner supernova core, where neutrinos have to diffuse out, then this volume cooling could take away energy which is otherwise available for the neutrino, the late-time neutrino signal, and so you wouldn't have enough power to power the late neutrino signal. So observing a long neutrino burst suggests that axions and other things couldn't have been so effective. That's sort of a standard argument applied to many cases over the years. For axions, there have been a lot of recent activity where people went back to the nuclear physics of the problem. Of course, axions are so interesting in the supernova context, because axions are QCD phenomena. The couple primarily to QCD, and therefore in a nuclear medium, neutron star cooling, supernova cooling is a crucial environment for axions to be produced. But the nuclear physics is kind of messy, and people have revisited this recently, or pions may play a role. And so there have been some recent revisitations of this problem. We have recently, following some lectures last fall in Lecce, written a big update of this review on astrophysical axion bounds, which I shamelessly advertise here. If you have nothing else to read this one. But what we are seeing here is the axion bounds as a function of axion mass, and these axions should be more massive than maybe 10 millielectron volts to be compatible with all of these constraints. And for the typical QCD axions, actually that supernova and neutrons are coolly bound is the most restrictive one, so it retains practical implications. It remains the most restrictive limit on these particles with these properties. So one, of course, then can ask what could be wrong about this if it's such an important bound. And of course, some people have argued that there's no real bound because we don't even understand the basic physics. They say supernova 87A maybe was a completely different event than we think, because a black hole might have formed, not a protoneutron star. And so there's that question where actually the neutron star supernova 87A, which has not been observed, right? It's not a pulsar. And so it's not a completely settled question, although this ALMA picture of this hotspot in the supernova remnant, behind which probably should be the neutron star, suggests there is a remnant, but it's not a black hole. But we don't know yet. So there's a somewhat open question, admittedly. Have we seen a real protoneutron? Of course, Thomas will say, I mean, there are many explanations why these alternative models must be wrong, but still it's kind of an issue one needs to follow. On the other hand, what we recently did and what Thomas already showed in his talk is that question when we say axions could shorten the neutrino signal of supernova. Actually, does the neutrino signal actually comply? Is already okay with standard models of supernova? And so what we found when we use at least these 1D models from the Garthian group, depending on different equations of state and different final state masses, then it turns out that typically when we plot the expectation of the signal as a function of time and energy for the IMB detector, sort of okay, but then for Kamiokande and Baksan, the late events are sort of not explained by these models. And so, as we already discussed after Thomas's talk, there's an issue of proneutron star convection that was not thought about so much in the olden days, which really shortens the signal. So again, another confusion in at least the non-expert communities that the speed with which energy is transported out of a supernova core is not dominated by diffusion; it's dominated by convection, which is also, we always say the diffusive transfer is the time scale, but actually the times are set by convection. Why these timescales are so similar is a question I defer to Thomas later after the talk. Okay. So then let me finally get to the final topic of flavor conversion of neutrinos, which kept many of us busy for a long time. So neutrinos, of course, can flavor convert in different places. So in the very olden days, we only talked about the usual vacuum or MSW conversions that would happen out here and can modify the supernova neutrino signal. Then a while later, one came up with these self-induced flavor conversion, these so-called slow flavor conversions driven by delta M square that might happen in this sort of outer region here. And then later on, we came around with these fast self-induced flavor conversions, the fast flavor conversions that we've discussed a lot here for the past 2 days, that may happen even deeper inside or they may overlap. So there's these different places and phenomena that can happen. And over the years, we got more deeper inside and more confused about what's actually going on in a real supernova. So let me just come up with a very brief history of this field. So the basic equations were set up in the early 90s, as we have discussed multiple times here. But then for a whole decade, people didn't think much about supernova. This question was applied in homogeneous media, and the main motivation were actually Samuel, the first to be credited for these collective oscillations and these self-induced conversions. They thought about the early universe and flavor conversion in the early universe past BBN. And so nobody thought much about doing this for supernova. And then around 2005, then in these key papers, Shen was actually here last week, people discovered that actually supernova one can have these self-induced conversions, and then one was looking for signatures of this effect. There were these so-called spectral splits where part of the supernova spectrum was swapped in flavor as a function of energy or not. But in all of these things, we didn't pay attention to the now trivial effect that you get spontaneous breaking of symmetry. So what was homogeneous to begin with doesn't stay homogeneous, and the same in this supernova context. Moreover, everybody tried to solving the equation as a boundary value problem, saying, there's this bulb, this emitting surface, that everything was kind of a function of distance, keeping it static, and that gives you correct solutions of the equation, or probably not the right solutions. And so then beginning 2015 or so, people became more aware this is actually space-time phenomenon. We have a partial different equation in space and time, and one should solve the complete problem with collisions, and then everything become much more complicated. First of all, because the time dependence was finally recognized to be important, and secondly, the fast flavor issue came in more at the same time. Though these two things got confused with each other, and it's almost like the same phenomena that these fast conversions, which depend on the angle distribution of neutrinos, which nobody had looked at before until Sawyer pointed this out. And it's similar to plasma physics and so on. So many questions that have opened up that we have hotly debated over the past few days here, that come up when we try to solve the full equations. So I'm sort of wrapping it up here, and let me just say, this has been a very difficult problem, but we should maybe console ourselves with this mathematicians' dictum: a problem worthy of attack proves its worth by fighting back. And the problem has been backfighting a lot at us, I think, over the past few years. So I conclude my talk with how any talk of mine on this subject concludes, which is, many open questions, and it's only the beginning, and we have to dig deeper to solve it. So that sounds maybe a little bit defeatist, but it's not. I mean, it's a very positive message in this, which means we should have many more TGI workshops on the subject, so that we could come here again to discuss these matters. And so on that note, I want to close and just thank everybody who is in the room, and especially, of course, the organizers of this fantastic meeting. So that's my conclusion. Thank you.
So that was really past, present, and future. Yeah. You promised and you did it. Okay. Maybe I have one comment.
Oh,
yeah, complementary to what you said. Maybe I think it would be nice to refer to the fact that the fast modes were first pointed out by Sawyer in 2000. Sorry. No, not 2015, but he wrote, as you know, a 2005 paper, where he was already considering.
It was that quantum entanglement speed up, not fast flavor.
There was he was finding a sort of fast flavor, considering a beam, two beam.
Yeah, but in the beam model, then that fast flavor is a speed up by, he called it speed up by entanglement. So that is a different story. I mean, as we all know, Damian. So when you have only two beams, you cannot have fast flavor conversion. At least not in the homogeneous case.
It was not head-on, but okay, maybe we can.
It's just two beams. You can never get fast flavor conversion.
He was
in the homogeneous limit. So I think what he did is something fast, something speed up. I think it's called speed up by entanglement or something. So I think this angular thing was I think 2015. I'm pretty certain about this, but I mean, I'm not taking away credit from him.
No. Okay, maybe we can rediscuss this. Okay.
I have two questions connected with the convection in the proton-neutron star, that plot that was also shown by Thomas. The first is that if you look at the density plot, it seems that only one point is not well reproduced by the model. No, for example, when I look.
You mean this question of the late signal?
No.
Here.
That one.
So this one. No. So the way is, of course, I mean, from the shading you can tell, but from the detailed analysis, I mean, in all these models, when we define the cooling speed or dilapidation speed, so basically up to like 7 seconds, okay, but everything after here, you cannot explain these three events. Until it's extreme.
But the color, I mean, the fact that the color is dark at low energy is an artifact of,
No, here that's the background here. But these things are much higher energies. And so one can, of course, play with the probability.
That's the background. Okay.
Yeah. So this is the supernova, and this is the background. And in Baksan, everything could have been background, but not so many events.
Okay, so it's too large. And I
and B had no background at all because at these high energies. So yeah, in principle, for example, one of these events like this one is usually interpreted as background. And these, of course, it's not logically excluded. They could be background, but if they're background, it's a large upward fluctuation.
Of the background. Okay.
So we played with this, and also, of course, once you go into detail, one cannot do it 30 years later because there's many questions. Are these events close to the edge of the detector or deep inside, and in the corner or not? So many.
So the data indicate that convection is too effective in
the conclusion is that convection, if the way it's done with the mixing length treatment, which Thomas now tells us is consistent with other tests, seems to tell us that these late events are very difficult, not completely possible, but very difficult to attribute to the supernova itself, if this whole convection treatment is appropriate. So this is a kind of open question. I mean, now we can't say if this is excluded by 10 to the -5 or 10 to the -6. I mean, it's very difficult to give an exact confidence level with these old data where you don't have information about, but we have information where these events are in the detector, and so it's not, one cannot post-process the old data, but just give on the basis of what they tell us in the old papers. We have a long appendix if you care to read. I think it's very difficult to attribute these to the actual signal.
The second question is what you suggested to ask is why convection time is why the convection time is so similar to the neutrino source.
Why is the matter and dark matter content of the universe so similar? I have no answer. I mean, if you leave out convection, you may get a cooling time which is 5 seconds longer. So it makes a difference, of course, opacity and convective effects. By the way, there is a lot of papers also on proto-neutron star convection showing tens of seconds of cooling times, and even without convection. And the point is that these works don't take into account nucleon-nucleon correlations in the opacities. We have done both. We had added the nucleon correlations already in our code 20 years ago, simulated from that time on all the models with nucleon correlations, but with convection, in particular in the 1D models, 3D has not been done at that time for these long times. It makes the signal even shorter, and you see the result here. I'm not so much concerned about the treatment of convection. I showed Georg a movie which Malte Heinlein, my student, sent me a couple of days ago, where we compared a 3-dimensional 5-second simulation, and convection, of course, is then taken into account hydrodynamically with the 1D mixing length treatment, and it agrees. So we see the models evolving on top of each other. So I'm not so much concerned about that, but the microphysics input in these simulations are equations of state. I mean, the equations of state we use are standard equations of states for the supernova business. Many people use them, SFHO, DD2, SFHX, Latimer-Swesty. Whether these equations of states are good with respect to the high density physics and with respect to the slope of the symmetry energy, which affects the evolution of convection. I mean, this is a nuclear physics question, not a question for the supernova modelers. Yeah.
Okay.
Just is a question on the same point. And so, by the way, thanks for the beautiful talk and a very useful one, in fact. But just on this point, so let me recall something very somehow well known, that in solar neutrino now we had the prediction with error bars since 60s. I mean, of course, the problem was much simpler than supernova simulation, but still we do not have prediction with error bars. So my question is this result a first step in the direction of producing a prediction with error bar for the time scale of emission? If it is so, I mean, I'm not sure you quoted a number in this case. The time scale of emission is, I don't know, 4 plus minus some second. I mean, we will need this in that analysis.
There is a table in the paper, in the appendix, where we actually give what we call T95. That is the time scale over which 95% of the neutrinos in number and in energy are emitted. We give a table. There's a table in the appendix.
For a series of models that we have done. So one cannot say what would happen for somebody else's equation of state or some
Yeah, sure. For what we, yeah, sure.
For your model.
For our models.
So
For
we
our
give
models.
we give all these numbers
Okay,
in the
okay,
table.
okay.
Yeah.
And of course, there is one caveat which one should not ignore. This is one-dimensional models. That means it doesn't model the three-dimensionality of the explosion and the corresponding fallback. This, for this reason, we have actually also pointed out in the paper that alternative possibility would be late Kamiokande events come from fallback. The onset of material falling back, of course, it requires a mass which is relatively large, larger than at the moment in some of the simplest models which try to predict that signal, so it would be a bit extreme, but I would not exclude it. On the other hand, what we want to point out here is, of course, the duration of the proton-neutron star emission, which is relevant for particle physicists when they make, let me say, constraints for particle models, particles produced, exotic particles produced in the neutron star, they rely heavily on the duration of the signal just coming from the neutron star. And that is the message here. Yeah?
Okay, thanks.
Yeah.
Thanks.
So I have a couple of questions for the community here and a couple of fast. Georg, full overview. Let me comment on the point that you said, never believe simulations. Yeah, I fully
didn't
join.
say never believe simulations.
No, I fully join you.
I said one should understand what one is seeing.
Yes, I fully join you, but your comment, your warning was for the neutrino energies increasing in Wilson's models, and shown his, let me say, breakthrough result of a neutrino-driven explosion, which we finally, of course, with more detailed models, with a lot of changes over history, numerical simulations, although you never can trust them, I fully join you, are really sometimes pointing towards the right direction.
I asked you to say you should never trust them. I just said when you see something surprising, you should understand it. And I guess Hans Bethe helped to understand this. I mean, one could take this much further. Like John Bacall used to say, never trust an experiment until it's been confirmed by theory. And so there's a similar thing. You never trust. I mean, numerics is maybe to some degree experimental because you can understand all the details immediately, but in the end you need to understand what the key things that are going on. So in that case, as you remember, maybe these rising energies of the mu and tau neutrinos was just completely unphysical. One could, in a very simple wave transfer, even I could do it, one could prove this cannot be true, right?
Yeah.
And I mean, I'm just saying sometimes there are certain ideas circulating in the community and you can't delete them anymore because they're going around, and this was going around for a very long time because in some sense, because also it was convenient, one hoped to have a very clear signal flavor conversion in supernova neutrinos, but these very strong energy hierarchies were just not true.
Yeah,
right?
No, I mean, I fully on the same side. Also, the talk be pointing towards some interest.
I mean, of course, my comment directed itself a little bit at some discussions we have had about these fast flavor and with these boxes or not, and how big or small and so on, and then I mean, especially with Damiano, because you cannot simply say, okay, I find numerically, so it's true. So if it's counterintuitive or even seemingly countering, I mean, then we need to understand what's going on.
Absolutely.
Right? So it's just
fully agreed.
It's not a waste of time to dig deep and understand.
And vice versa, it's not a waste of time to do these kind of
exactly. One has to explore, but then also the slow ones like us have to catch up and understand what's actually.
I want both parties getting their credit. Another comment was on the SASI, which is really very important now. I think with these also the measurement of SASI modulations on the neutrino.
SASI is also an example for something that was discovered numerically. I understand, but then there was a real beautiful explanation for what's actually happening, right?
behind it. But measuring the neutrinos, signal modulations would really be very interesting, because the occurrence of the SASI depends on the shock evolution. And so one could really, if one had a neutrino signal from a galactic supernova, one would have a possibility to now say whose models are on the right track and whose models may not be compatible with that measurement. SASI, for example, in the Fornax simulation, instability to grow.
So one message which I didn't say explicitly here, but I mean in the olden days when these first measurements were made and we knew nothing about neutrino parameters, then every thought we could use, for example, supernova neutrinos to learn about neutrinos and the mixing parameters. But now we know them very well, except for some missing bits which we will get soon, and so maybe the whole thing has turned. Now we want to use neutrinos to learn about the supernova, the next galactic supernova, like the SASI, and then it's fantastic that we have all these ingredients of neutrino mixing from the laboratories. So the whole logic of the field has sort of turned upside down.
Yeah.
It's just sometimes some communities think, okay, if you learn some astrophysics from such observation, it's boring. But I mean, I think it's very intriguing. In some sense, finally, people have measured the neutrino mixing parameters, so we can use them as a messenger to learn about the sources, right? Which is the same way that gravitational waves are now used. We don't want to learn about gravitational waves as such, right? We want to learn about the sources, what's going on there. You want to use gravitational waves for astronomy, and here one could use neutrinos for maybe probing nuclear physics, equation of state, or whatever you guys are uncertain about, right?
Yeah. So now my question, I mean, actually, who moins? I know. But than me on what he wants to discuss in these papers. But he claims that all this analysis done more recently on the fast flavor conversion in supernovae is just flawed. So, I mean, what's the common understanding about this? I mean, does he make a point which is relevant, or is it just off track?
The problem is already that I don't understand his notation because he doesn't explain it. So I have not more to say on that.
But I think it's mostly about this many-body quantum entanglement that he ultimately worries about, I think, which of course other people have also worried about. Quantum entanglement, you know, the many-body few.
Thanks, but yeah, I have to say that his notations are peculiar, and I'm not fully convinced of what.
Sawyer is claiming that there are no fast flavor conversions.
Not necessarily, but he just. Damian, you want to say something?
He has two claims, right? One that
I mean, but from the phenomenological point of view, I think one of his most important claims is that there will be some instabilities which are faster than the fast instabilities, so just anti-neutrino instabilities. I mean, the content of his PhD paper was mostly that there would be instabilities faster because they convert neutrinos into antineutrinos, but then we showed that these are alicity non-conserving, right? So that's one thing that I think is settled. I mean, he doesn't believe it, but we think it's settled that that couldn't happen. And the many-body, I think, yes, I mean, the many-body argument in his papers is used as a seeding for the fast instabilities, but I don't think anybody clearly understands this point in his papers. But one of his points, I think, is settled, which is this new anti-new conversion that he was proposing, which seems to be alicity non-conserving, so just not true.
I mean, maybe this we should rediscuss. I'm not fully convinced of what you wrote, but okay. We can do it offline.
Okay, so
This, yeah. Rebecca.
Thanks so much for this. It was very engaging, except I can't help Notice you did not mention nuclear. What's happening? Can you hear me?
Yeah, now
Yeah. So you didn't mention anything about nucleosynthesis, really. Yeah?
because I don't know anything about it.
Yeah. Okay, that's fair enough. But I'm wondering if you have an opinion on what the neutrino-driven wind are like, what kind of electron fractions we would expect in this environment because of the neutrino physics.
Well, because we haven't fully solved that problem, we are still struggling.
Right, it's clear we haven't,
what can I say?
but what is the error bar, would you say, due to the uncertainties in the neutrino physics? Like, how low can it get and how high can it get?
That is as difficult as the question that
Yeah, I'm just wondering if you have an opinion. Yeah.
your question is has a difficult answer as much as the question that was raised by Thomas yesterday. It deserves a full discussion. Okay.
Yeah, I mean, of course, I can give a rough comment, but Georg is, of course, right with the study in order to be terminology. I don't like that anymore. The wind occurs in certain supernovae, the lower mass ones, but in the more this multidimensional around the neutron star for a long period. Called 3D version. I think this is the right term because this flow is not determined by proto-neutron star properties, as in the case of the neutrino-driven wind, where the proto-neutron star determines the neutrino emission and the wind outflow is just depending on the proto-neutron star properties. This three-dimensional flow is dependent on the progenitor infall, and there is a different physics behind it. Anyway, the YE is, of course, determining or setting the YE is a competition of electron neutrinos and antineutrinos. In the modern niche models, the spectra are not so much different anymore. So I would think, as Georg mentioned, that this hierarchy of neutrino energies, which was seen in the Wilson models, has become much, much lower. And in particular, after the explosion has set in, the neutrino spectra become very similar. There is still a small gap between electron neutrinos and antineutrinos, but the mu and tau neutrino spectra and the electron antineutrino spectra are very similar. So when you then flip these flavors, I think what you will produce in supernovae in future models with flavor converters will be pretty similar to what we get now, namely a lot of iron group-like elements and maybe the low mass trans iron elements up to the strontium, yttrium, and zirconium peak, which is pretty easy to produce because you don't need a high on neutron rich. Yes, you are with a YE 0.5. I guess that the detailed analysis we have done will probably not change that. That's my guess.
Okay, so 0.5 plus or minus.
Yeah, I mean, yeah. 0.5 plus minus 0.1, yeah.
I think that would deserve also discussion.
I have a question related to this the operation. So yes, reverse the discussion we had. Thomas was before about the uncertainties about on the equation of state. Can you reverse the question and say what would it take for the equation of state to get longer signal duration? Would it be completely unreasonable to make that in agreement with that?
I mean, we've played with the equation of state on the market or available to the group, and it's all consistent with the same conclusion. If there's an extreme one that could mimic
so you mean that the variations on reasonable equation of states do not change significantly that?
Give this, but how can you prove there couldn't be one other example that would...
Well, so one has to make several comments. The equation of states currently on the market, they are relatively, I would say, robust with respect to their properties up to about 1.5 to 2 times nuclear matter density. Because the parameters used in that regime for modeling the mean field properties of the nuclear medium, they are constrained by observational properties and measurements, and they are also constrained by astrophysical properties of neutron stars. And those seem to be compatible. beyond the twice nuclear matter density regime, they are extremely uncertain. It's just an extrapolation. So what could be the modification to explain the last three events, if there were a phase transition, for example? And I'm pretty sure that nuclear physicists could construct phase transitions which heat the neutron star again, release internal energy in the neutron star, and extend the signal longer. I'm pretty sure they could do it. Okay. I mean, they have done that in extreme cases, for example, for quark, hadron-quark phase transition, work by Tobias Fischer, by David Blaschke and collaborators, following up previous work by the Basel group, Sagat, I think, Irina Sagat, if I'm not mistaken. The Blaschke group has modified the equation of state so that it's compatible with other constraints, and they found a late phase transition which could even then trigger a supernova explosion for very massive neutron stars. So that kind of extreme physics wouldn't be needed. A modest phase transition leading to internal energy release, so a first order phase transition in the neutron star medium could actually reheat, and the energy is moderate, which you need, some 10 to the 52 ergs. It's not excessively large. Yeah.
Okay. Thanks.
Okay, if there are no more questions or comments, let us thank Georg again.